For decades, the idea of searching for intelligent life beyond Earth was closely tied to the hope of receiving a signal. Scientists set up vast radio dishes to scan the skies, listening for faint whispers that might come from another civilization. The approach was straightforward in concept. If another world had the technology and the intent, perhaps they would broadcast their presence. Radio telescopes became the symbol of the search, and projects like the SETI program focused on filtering out the natural noise of the universe to identify something that could only be artificial. For a long time, this approach defined how we thought alien contact might happen. A transmission, a pulse, or a repeating pattern would serve as proof that we were not alone. But this idea has always been a narrow one. It assumes that other civilizations use radio, that they want to communicate, and that their transmissions reach us in the small window of time when we are listening. In recent years, a new possibility has come into focus. Rather than listening for signals, scientists have started to consider that the strongest evidence of other civilizations might arrive in a very different way. Instead of sound or light, the evidence could be physical objects, things that cross the space between stars and make their way into our solar system. Unlike a fleeting radio transmission that disappears once it is missed, an object can persist. It can be observed, measured, and even captured if circumstances allow. The discovery of interstellar objects has made this shift in thinking much more than a theoretical exercise. Until 2017, there had been no confirmed detection of any solid body entering our solar system from another star. Then, astronomers noticed something strange. A small, elongated object passed by at a speed and trajectory that made it clear it did not originate here. This object was given the name Holomua, which means scout in Hawaiian. It was the first confirmed interstellar visitor. 2 years later, another arrived. This one was clearly a comet, with the familiar tail of gas and dust. It was named Borisov, after the amateur astronomer Gennady Borisov, who first spotted it. Both of these detections were extraordinary. Statistically, they are extremely rare. For every 100 billion comets that orbit our sun, only a handful are thought to come from beyond. The fact that we have identified more than one in such a short span of time suggests that either we are becoming better at noticing them, or the universe occasionally delivers these visitors in clusters. The arrival of these objects changed the conversation. They are not signals. They are material, physical bodies that can carry information about the systems they came from. In a sense, they can act as natural messengers. Some scientists have gone further, pointing out that if there were ever to be artificial probes or fragments of technology drifting between the stars, they might look very much like these visitors. Even if no advanced technology is involved, the chance to study material from another star system is a scientific gift. Against this backdrop, the detection of a third interstellar object, designated 3I/Atlas, has drawn intense interest. The name indicates that it is the third such object on record. Like its predecessors, it appears to have arrived from interstellar space, crossing the gulf between stars before entering our solar system. On the surface, one might expect it to behave like a typical comet, brightening gradually as it comes closer to the sun and releasing gas and dust in predictable ways. However, the story of 3I/Atlas quickly became more complex. Its brightness increased 5 times more than expected in a very short span of just a few weeks. This is not what standard cometary physics would predict. Normally, a comet's light output is controlled by how much sunlight it receives and how much ice and dust it releases as it warms. In this case, the increase in brightness was far too rapid to be explained by geometry alone. When astronomers turned their spectrographs on the object, they found another surprise. The light signature indicated the presence of nickel, a metal that can be forged in violent cosmic events such as supernovae, or the formation of planetary cores. At the same time, there was a puzzling lack of iron, which is normally found in tandem with nickel in natural objects. No comet observed in the solar system has ever shown such an imbalance. On top of this, the trajectory of 3I/Atlas presented its own mystery. Comets with active tails usually show small but measurable shifts in their path, as jets of gas push them slightly off course. This effect, called non-gravitational acceleration, is a reliable feature of active comets. In the case of 3I/Atlas, though, the object barely deviated from a gravitationally determined orbit. It seemed almost unaffected by the outgassing that was clearly visible. Taken together, these factors raised questions. If the object is natural, then why does it behave so differently from the comets we know? If it is not natural, then what could explain the anomalies? It is important to note that extraordinary claims require extraordinary evidence, and so far no one can say definitively that anything artificial is involved. But even without invoking such explanations, the data itself is difficult to reconcile with current models. This is why scientists are paying close attention. Each interstellar object represents a unique chance to study material from another solar system. The rarity of such detections makes every case significant. Even a single anomaly in brightness, chemistry, or trajectory can challenge our understanding of what is possible in nature. The broader point is that the search for extraterrestrial intelligence may need to expand its scope. For decades, the emphasis has been on signals, under the assumption that communication would be deliberate and detectable. But physical objects, whether natural or artificial, may hold as much or even more information. A radio signal lasts only as long as it is transmitted and received, but an object can persist indefinitely, crossing the cosmos long after the civilization that launched it has changed or vanished. The discoveries of Humuma, Borisov, and now 3I/Atlas demonstrate that interstellar visitors are not merely a thought experiment. They exist, and they pass through our solar system from time to time. Each one is like a ticket in a cosmic lottery, a rare opportunity to observe something that has traveled across unimaginable distances. The fact that they do not behave uniformly only deepens the intrigue. As 3I/Atlas continues its journey, astronomers are working to gather as much information as possible. Large observatories and survey programs are complemented by smaller teams and even amateur astronomers, who often help to spot anomalies in data archives. Together they piece together the light curves, spectra, and trajectories that form the basis of our understanding. While interpretations may differ, the facts remain: this object has brightened far more than expected, shown a surprising chemical composition, and resisted the typical shifts in orbit seen in comets with visible tails. These observations do not yet form a complete picture, but they suggest that the universe still has surprises in store, even in phenomena we thought we understood well. On the 7th of May 2025, the Transiting Exoplanet Survey Satellite, better known as TESS, recorded something unusual. Against the dense backdrop of stars near the galactic center, a faint and fast-moving object appeared. At first it went unnoticed. The satellite generates vast amounts of data, much of it crowded with stellar noise and clutter, and the motion of this object was subtle enough to escape the automated alerts. Its faint glow blended with the thousands of other points of light. Only later, when astronomers reviewed the images, did the traces begin to stand out. Over the next month, the object continued to move steadily, captured night after night in full-frame images stored on the satellite's hard drives. Each image on its own showed very little, but when stacked together the trail became clearer. The breakthrough came on the 1st of July, when the Atlas survey, scanning from its Chilean site at Rio Hurtado, flagged the anomaly. By then the object had brightened significantly, far more than was expected for its distance from the sun. In fact, it was shining about 5 times brighter than when TESS had first recorded it. Once the alert went out, observatories around the world pivoted quickly. Within a day, telescopes were trained on the moving light. At the same time, teams began to comb through older data from other surveys. The Zikwi Transient Facility in California and Pan-STARRS in Hawaii both found earlier images of the object dating back to late June. Amateur astronomers also played a role, digging into public archives and recovering additional images that help fill in the missing weeks. By combining all these observations, researchers could build a detailed light curve that charted the object's rise in brightness over time. The results were clear. Between early May and early June, the object had brightened by a factor of 5. Standard models of cometary behavior could not explain this. At a distance of more than 6 astronomical units from the Sun, water ice should remain frozen and activity should be minimal. A modest increase in brightness, perhaps 1.5 times, would have been expected as it drew slightly closer. Instead, the change was dramatic and steady, and it could not be dismissed as an instrumental error. The measurements from different telescopes agreed with one another, with error bars too small to explain away the surge as random noise. This was the first major anomaly. A comet-like body, active at a distance where comets should remain quiet, was behaving in ways that challenged the established playbook. Some suggested that perhaps the object was using energy in an unfamiliar way, or that its composition allowed activity at much lower temperatures than usual. Others raised the more speculative idea that the brightening might not be natural at all, but instead the byproduct of an engineered process, something akin to braking or deceleration. Such claims are controversial, and astronomers stress caution, but the data left little room for simple explanations. Attention then turned to the chemical makeup of the object. Spectrographs at the Very Large Telescope in Chile were tuned to capture the faint emissions from its coma, the cloud of gas and dust surrounding it. What they found was unusual. Nickel lines appeared clearly in the spectra, yet iron lines, which should accompany nickel in nearly all natural contexts, were absent. This imbalance is not seen in comets within our solar system. Typically, iron and nickel are present in a ratio of about 18:1 in favor of iron, reflecting their shared origins in stellar processes. Even in the dustiest and most metal-rich comets, nickel does not exceed iron by more than a factor of 2. In the case of 3I/Atlas, the ratio appeared to exceed 15:1, and possibly even higher. Teams rechecked their calibrations, stacked exposures, and compared the results with laboratory data. The result held steady. Nickel was there, iron was not. Natural explanations were proposed, including selective release of nickel-bearing compounds or exotic processes during the object's formation. But none fit perfectly, and the possibility of an artificial residue, such as nickel-rich alloys eroded by ancient technology, could not be fully dismissed. The third anomaly lay in the trajectory. When comets release gas, the outgassing acts like a series of tiny rocket engines, pushing the nucleus slightly off its predicted gravitational path. This effect has been measured in many comets, and can be significant. For Borisov, the interstellar comet observed in 2019, the deviation amounted to about 100 kilometers per day. For Oumuamua, the first interstellar object in 2017, a sharp non-gravitational acceleration of tens of thousands of kilometers was detected, even though no gas or dust was visible. 3I/Atlas, however, showed the opposite pattern. It displayed a visible coma and tail, clear evidence of outgassing, yet its measured deviation was barely 1 to 1.5 kilometers per day. Its trajectory remained almost purely gravitational. This mismatch between activity and motion is difficult to explain. Either the object is far more massive than its brightness suggests, making it resistant to small pushes, or some other mechanism is suppressing the effect of the jets. No natural explanation has yet fully accounted for this paradox. The combination of these three anomalies, rapid and excessive brightening, an unusual chemical fingerprint, and a lack of expected non-gravitational acceleration, has made 3I/Atlas one of the most puzzling objects ever observed. None of these findings on their own would be enough to suggest anything beyond the natural, but together they present a picture that does not easily fit within current models. For comparison, Borisov behaved largely as a comet should. Its coma and tail followed the rules, and its deviations were in line with what astronomers would expect from outgassing. Oumuamua, on the other hand, had no visible coma, but showed a strong trajectory change, which remains unexplained to this day. Now 3I/Atlas seems to reverse the situation, with a prominent coma, but almost no measurable drift. Taken together, these three interstellar visitors form a set of contrasts that challenge conventional understanding. Looking forward, astronomers are keenly aware of how rare these opportunities are. The Rubin Observatory in Chile, with its wide-field legacy survey of space and time, is expected to revolutionize the search for such objects. Its sensitive and frequent scans of the sky will make it much harder for interstellar visitors to pass unnoticed. Future detections may allow scientists to gather data earlier, track the objects longer, and perhaps even prepare missions to intercept them. For now, though, the study of 3I/Atlas relies on a combination of large observatories, survey programs, and contributions from amateur astronomers. In fact, some of the earliest and most useful reconstructions of the light curve came from enthusiasts who sifted through archival data, adding crucial points to the timeline. The collaborative nature of this work underscores how astronomy today is not limited to professionals alone. With the right tools and shared data, the wider community can contribute to discoveries of global significance. As the observations continue, the debate remains open. Some scientists prefer to emphasize natural explanations, however unusual they may be. Others see the anomalies as a reason to keep an open mind about more extraordinary possibilities. Either way, the data gathered so far ensures that 3I/Atlas will remain a subject of study and discussion for years to come. In the end, the importance of this object is not whether it proves the existence of extraterrestrial technology. What matters is that it demonstrates how much we still have to learn about the universe and the processes that shape it. Even in a field as old as astronomy, where comets have been observed for centuries, the unexpected can still appear. Each anomaly is an opportunity to refine our models, question our assumptions, and broaden our perspective. The search for life beyond Earth is not confined to a single method or expectation. Radio signals, laser pulses, chemical imbalances, and interstellar objects all form part of the puzzle. The arrival of 3I/Atlas reinforces that the universe does not always behave according to our expectations. Sometimes the strongest clues come not as messages, but as mysteries carried by objects themselves. The challenge is to recognize those clues, study them carefully, and remain open to the possibility that the evidence of other worlds may already be passing us by.